In this video lesson, we're going to be looking at content in Chapter 3, Section 2. We're going to be looking at polynomial functions and their graphs. Before we actually get to this page, I've made a copy of page 365 from the textbook. Let's get a little bit of background about polynomial equations and graphs of polynomial equations. So we've worked a little bit with polynomials. We've looked at quadratic functions, which are polynomials. All right, and then on this page right here in our textbook on page 365, here's a definition of a polynomial function. So we have a definition. We want to look at this equation right here. It's a little bit scary just because of all the letters, etc. But what we want to take away and remember from our previous study is that this is called a polynomial function of degree n. And the reason we call it a polynomial function of degree n is because when we look at the variable x in this big ugly equation here, the highest exponent is actually this number n, whatever it is. Because when we look at this next term right here, we see that the exponent is n minus 1, and it just continues down that way where our exponents get smaller, smaller, and smaller, etc., until we end up with a constant number, a term that doesn't have a variable x in it. So this is called a polynomial function of degree n. The number a subscript n is called the coefficient of the variable to the highest power. It's called the leading coefficient. So just some terms right here. So polynomial function of degree n just means look for the highest exponent in the equation, and that's what we call the polynomial, a degree 5 or degree 6 or whatever. All right, the number a sub n, a subscript n, okay, notice that a subscript n represents a number, and it is the coefficient on what we call the leading term. The term is the term that has the highest exponent in that polynomial. So anyway, a leading coefficient, a sub n. More work with that in a minute. All right, here are some equations of polynomial functions and not polynomial functions. So as a reminder, with the polynomial function, we need to have integer exponents and real coefficients or constants. So this is a polynomial function because this exponent is 5. It's a whole number. Number 2 right here is a whole number. The square root of 2, the square root is not over the x. The square root of 2 is a real number. I don't see any lowercase i's to suggest imaginary numbers. We would call this a polynomial function of degree 5 because the highest exponent is 5. Some other ideas here is that the leading term, the term that has the most impact, if we were to plug in numbers for x, the term that has the most impact would be this term right here because it has the highest exponent. So this is called our lead term, our leading term. And the coefficient on this leading term, called the lead coefficient, would be -3. So the whole thing is the term, but the number in front of the variable to the highest exponent is called the lead coefficient. All right, here we have another polynomial equation. Okay, notice that g of x is equal to -3x to the 4th times the quantity x minus 2 times the quantity x plus 3. What happened from this line down to this line is that these two binomials were multiplied together by using FOIL, and the result was this trinomial. And then notice from this line to the final line, they distributed in the -3x to the 4th and multiplied it into all these terms. And here is the result. So this is also another example of a polynomial function. It's a degree 6 because that is the highest exponent I see. The lead term is -3x to the 6th, and the lead coefficient is -3. Okay, why did these equations fail to be polynomials? Well, if we look at this first term, notice the square root is over the variable. So that's going to result in r having x to the 1/2 power. Those are equivalent. The square root of x is equal to x to the 1/2 power. And here's why. If you look underneath the radical called the radicand, the understood exponent is 1 here. The understood root is a 2. We just don't usually write those 2 in. So this is equivalent to rewriting this with a fractional exponent as x to the 1/2. Another kind of side example, what if we had the cube root of x? How do I rewrite that without having a radical? I say that that's x raised to the 1/3 power. What if it was the 4th root of x? Well, then I say it's x raised to the 1/4 power. All right, what if we had the radical x squared with the cube root? Well, we rewrite it as x raised to the 2/3 power. And notice that all of these exponents are not whole numbers. So we fail to have a polynomial if we have this kind of structure right here. So not a polynomial. All right, it's not that the issue is the square root of 2. The square root of 2 is a real number coefficient, and that's okay. All right, this is not a polynomial because of this first term right here. If I wanted to rewrite this term without x being in the denominator, I could bring up the x to the numerator with -3, but then I'd have to adjust and make that x squared a x to the -2. So again, that's not a whole number, that's an integer. It's a negative whole number, so that fails to be a polynomial. All right, so, and there's a little more information here. A constant function is like a flat line. It's just a straight line across the coordinate plane. If we have a constant function, it is a polynomial function of degree 0. And here's why on that one. Let's say I had the constant function f of x equals 5. Okay, its graph would look like this. All y's are 5. So I go up from the origin to 5. I'll call that 5. And when I graph, I'm going to get this constant function. The degree is 0 because I could put in here an x to the 0 power. And from a long time ago, we saw that anything to the 0 power is 1. So in fact, I'm just bringing in x to the 0, and it's just a kind of a clever, silly kind of form of 1. So I wouldn't usually write it this way, but we can see that it is a polynomial because we have a whole number as an exponent and the 5 is a real number. All right, a linear function graphs a straight line, okay, and we can see that on this variable x, its exponent is 1. That's a whole number. Okay, m is going to be a real number and b is going to also be a real number. M tells us about the slope of the graph of this linear function and b tells us the y-intercept. This is going to be a degree 1 polynomial. A quadratic function, which we've already seen in general form, looks like this from our previous work. The highest exponent is 2, so it's a second degree polynomial, and all the coefficients are real numbers. But in this section, we're going to focus on polynomial functions of degree 3 or higher. And we're going to be looking at some behavior of those third degree or higher polynomials. All right, so we looked at some equations of polynomials and not polynomials. All right, a little bit more background about some of the graphs that we're going to be looking at. All right, polynomial functions have what we call smooth, continuous graphs. Smooth and continuous. Smooth means that the graphs contain only rounded curves with no sharp corners. Continuous means that the graphs have no breaks in them and can be drawn without ever lifting your pencil from the rectangular coordinate system. All right, graphs of polynomial functions and not graphs of polynomial functions. Okay, here are some graphs because these graphs right here, when you start drawing them from far left, that's usually the way we start drawing, we can draw this without ever lifting our pencil. And notice that any turning points are smooth and rounded. Same thing here. This graph actually comes down, okay, and then it kind of turns around again, and then leaves the screen or the graph going off into infinity. So these are polynomial functions. There's no breaks in them. There's no sharp turns. Okay, here are two examples of not graphs of polynomial functions. So right here, we have a break in this graph. If I'm trying to draw this graph, I've got to lift my pencil right here at this x value and jump down and then continue drawing the rest of the graph. That's not a polynomial function. So we'll look at this a little bit later in a different lesson, something that has a break in it. But right now we're focusing on these types of graphs. And this graph has two sharp turns, so it can't be a polynomial function. All right, well, I'm hoping that some of this background is going to help us with the content that we need to look at, okay, back here in this handout. All right, so polynomial functions and their graphs. So this equation right here defines a polynomial function. We've seen it. It's a little ugly because there's no numbers in there, but we will be looking at some specific examples in just a minute. Polynomial functions encompass all functions with real coefficients and exponents that are whole numbers or non-negative integers. The highest power exponent is the degree of the function, and the coefficient of this term is called the leading coefficient. So here are some more examples of polynomials. This is a linear function because the highest degree, the highest exponent is 1. It's that understood 1 there. And the leading coefficient is 3. The lead term is 3x, but the coefficient is just 3. In the second example, be careful because they're kind of tricky here. Notice that the highest exponent is 3. This is a cubic. It's degree 3 polynomial. The leading term is going to be negative 2x cubed, because I could rearrange these two and switch the order. But the lead term is this whole entire term, but the lead coefficient on that term is negative 2. This is a non-example of a polynomial, okay, and that's because the coefficient of x to the 4th, right here, has an imaginary component to it. Right, and this is not a polynomial equation because I need to get x out of the denominator. If there's an understood 1 exponent here, if I want to bring x out of the denominator, I adjust to make its exponent negative. Well, a polynomial can't have negative exponents. Okay. So it says look in your textbook for other examples, and that's the page I just shared with you. All right, polynomial functions of degree 2 or higher have smooth, rounded, and continuous graphs. We saw that. Okay, they change direction at what we call turning points. So it says a function of degree n can have at most n minus 1 turning points. Okay, I think a perfect example of that would be the quadratic equations we studied in the previous section. For example, if I had this quadratic equation, I'm just making this up right here. Okay, we know that the quadratic equation produces a parabola. Well, how many turning points are on one of those parabolas we saw? Well, there's only one turning point. Okay, if the parabola opens upward, we have that absolute min at that turning point. If the parabola opens downward, okay, then we have a turning point right there at that vertex or that absolute maximum. So I hope I said minimum here, and this is maximum. So the degree is 2, but at most, I'm only going to have one less than 2 or one turning point. So if I have a 6-degree polynomial, I might have 5 turning points on that graph. All right, we're going to be studying a couple of things about polynomial functions of degree 3 or higher. One of the things we're considering is end behavior. The ultimate objective of this whole section is, given a 3rd degree or higher polynomial, can we use some things that we know about that equation to help us draw a graph, to help us sketch a graph? So our objective is to sketch graphs. But first we have to dig into what's going to help us do that. Well, one of the things we're interested in on 3rd degree higher or higher polynomials is what is the end behavior of the graph? Which means what is the graph doing as x approaches the negative infinity and the positive infinity? So what's happening to the far left and to the far right? Okay, not so much what's in between, I can handle that later, but how do we know how this graph maybe comes on the grid and how it leaves the grid? And we can determine this end behavior by what we call the leading coefficient test. Okay, and there's a lot, but once we get our mind around, what's going on, we just have to do a little bit of memorization and we'll be able to answer the end behavior question. All right, functions with degrees that are even numbers like 2, 4, and 6, okay, they share end behavior characteristics. So a 2nd degree, 4th degree, 6th degree polynomial all are going to have kind of similar behavior at the far left and far right of their graphs. And then degrees that are odd numbers, so like a linear function or a cubic or a polynomial that has the highest degree of 5, they all kind of share similar situations. All right, we also need to be aware of what's the sign of the leading coefficient. Okay, is that leading coefficient positive or negative? And this also contributes to the behavior. Okay. All right, I know this didn't really show up very well on mine, but let's see. I think this is called n is even. So let's say that we're dealing with an even degreed polynomial. Okay, but what if the lead coefficient, which is a subscript n, what if it's positive? And this is n is even, but the lead coefficient is negative. And then this is our other situation. What happens when n is odd? We have an odd degree polynomial, but the lead coefficient is positive. And the fourth and final case is when n is odd, but the lead coefficient is negative. All right, well, what I'm going to try and do is kind of share with you something that you can kind of memorize that might help you with some of our work today. First of all, let's consider y equals x squared. I'm going to put y equals x squared here. I'm going to put y equals negative x squared here. I'm going to put the equation of the common function y equals x here, and I'm going to put y equals negative x here. You might remember that y equals x squared is that parabola that kind of follows these arrows, but it's more rounded. Y equals x squared is more rounded. Y equals x squared behaves like this. So n is even. If n is even, 2 is even, and a subscript n, which is 1, is positive, then both my ends of my graph are going upward, following this kind of pattern here. So how do we describe the end behavior? Well, over here, we say that this graph is rising on the left. It rises left. So we're on the left part of the graph, and it rises. Okay, well, over here, the graph is rising. It rises right. So both arms are going up, so to speak. What happens when we take an even degree polynomial, but we put a negative lead coefficient? Well, think about the parent function, x squared, being reflected across the x-axis. So that would look something like this. It has this kind of behavior, where the behavior at the ends here are modeled by these two arrows. So when n is even, but the coefficient is negative, then I can say that I fall left and I fall right. Falls left and falls right. So for these two cases, we want to identify that do we have an even degree? If we do, is the coefficient positive or negative? Because either both arms are up or both arms are down. Now we have to consider what happens when we have an odd degree function. Well, I want to use these simple graphs right here to help us understand, no matter if I have an odd number of 1 or 3 or 5, that the ends of the graph of those functions will all behave the same. So we know this is an understood exponent of 1. It's odd. We know the lead coefficient is positive. It's 1. We know the degree is odd, 1, but we know this lead coefficient is negative 1. Let's think about the graph of y equals x. Well, y equals x, if I were connecting right here, this gap would look like this. So when I look at the behavior on the left, I see that it's falling. So I fall left and I rise right. So for y equals negative x, which would be this graph reflected across the x-axis, it would have this behavior. So an odd degree has opposite ends like this. An even degree has the ends going both up or both down. So y equals negative x to the first degree would look like this. We rise left, rises left, and falls right. So when I'm asked to find end behavior and my degree is odd, but it's bigger than 1, then I look at one of these two cases right here. I can eliminate these two cases to describe the end behavior. And depending upon that odd degrees function's lead coefficient will determine if I fall left or rise right. And then we have the other two cases here. If I have an even degree, I know that I can eliminate these odd degree graphs. If my lead coefficient is positive, I know we rise left and rise right. If the lead coefficient is negative, I know that I'm going to say falls left and falls right to describe the end behavior. So down here, we just have some extra examples that kind of tie all that together. So these are even degree polynomials. All of them are right here. This is with a positive leading coefficient, so that means that both the ends of the graph are rising. So rises left, rises right. Right here, we can see rises left, rises right. So whatever equation produced this, it has to have a high exponent that's even with a positive coefficient. Okay, notice that both of these ends are going down. So we have falls left, falls right. This is an even degree polynomial with a negative lead coefficient. Same thing here. Both ends are going down, so falls left, falls right. It must be some even degree equation with a negative coefficient. Okay, and the last situation over here is what if we have odd degrees? Notice that the end behaviors aren't both up or both down. They go in opposite directions. So for an odd degree function, it must be if I have a positive coefficient. Think about this graph. Always kind of connect back to these four main graphs that I'm going to try and memorize and help me understand other equations. If I have an odd degree with a positive coefficient, I'm going to fall left. Yep, this graph's falling left and rises right. This one's falling left and rising right. So just examples of odd degree functions. Okay, these are odd degrees because the end behaviors are going in different directions, but because I'm rising left and falling right, okay, it must be that I have a negative coefficient to really closely resemble what's going on here. And then same thing here. Odd degree, negative coefficient. Rises left, falls right. Whew. I know that's a lot, but hopefully that will help us understand how to graph some things. So, all right, so let's come over here to some examples. It says, use the leading coefficient test to determine the end behavior of the graph of the polynomial function. So the leading coefficient test means we have to first determine, do we have an even or an odd degree polynomial? And in front of that lead term, is that lead coefficient positive or negative? All right, well, the degree here is 3. It's odd. So that means that the opposite ends, the ends of the graph on the left and the right, are going in an opposite direction. What's the lead coefficient? Well, the lead term is 11x cubed, but 11, the positive number, is what's going to tell me, okay, how I'm going to draw that graph at its ends. So odd degree, positive. I always think, okay, well, what equation is that that's going to help me answer the end behavior? Well, odd degree, I'm going to think about the 4 equations I wrote on the previous page. I'm going to think about odd degree being this equation. Positive coefficient, that would be y equals x. If I can quickly memorize that, draw it down here, I can respond to the end behavior for this third degree and say falls left and rises right. All right, let's look at example 2. First of all, if I'm asked what's the end behavior, well, I need to find the highest exponent. It's a 4th degree polynomial. The lead term is negative 5x to the 4th. The lead coefficient is negative 5. So it's even. So then I think about, okay, that's 4 equations. Okay, if I have an even degree, it looks like y equals x squared. But because my lead coefficient is negative, I'm going to think of the negative x squared graph. Have I memorized it? Well, I know it looks like this. So we fall left, we fall right. So this graph will have the same end behavior as this graph right here. Okay, moving on. Next, we're going to find zeros of polynomials, and we've actually done that already. Zeros are also called x-intercepts, and it's the value of x when y equals 0. They're also called root solutions of the equations. All right, we find zeros by setting the equation f of x equal to 0 and solving for x. Sometimes equations can be solved by factoring. All right, so for problem number 1, find all zeros of this function by factoring. So I'm going to work from far left over here to use all this space. So when we were finding x-intercepts before, which is what we're finding here, which are zeros, okay, we set y equal to 0. So f of x is 0. Okay, if I'm going to factor this, the first thing I'm going to look for is a greatest common factor. Well, I don't see that I have a number or a variable that comes out of each of these four terms. So then my next thing is, okay, what do? Well, if I've got four terms should trigger in our brain that we're going to try and factor this by grouping. So let's group the first two and the last two. And remember, because this minus sign is being separated from the 4x, we also have to adjust and put a +8. All right, let's take out the common factor. So don't forget the 0 equals. X squared comes out, and I'm left with x plus 2. Check by distributing. Over here, take out a 4. Well, success, I have the same parenthesis. So let's factor out the x plus 2. And I'm left with x squared minus 4 in the second parenthesis. So let me bring that up over here. And I'm going to trade sides at the same time. But x plus 2, x squared minus 4 equals 0. Okay, so now I can set each factor equal to 0, but wait, I see that I could probably factor this into the sum and difference of like terms. This will break apart into x plus 2, x minus 2. I could certainly do that if I wanted to, but I think I'm going to solve it by using the square root property. So since I've factored, let's go ahead and set each factor equal to 0. So this factor is going to give us a solution of -2. So -2 would zero out that factor. So one of our zeros is x equals -2. Over here, x squared minus 4 equals 0. I'm going to use the square root property, so let me add a 4 to both sides. So x squared equals 4. And just the good math here, remember, bring in the square root on both sides of the equation. Even roots means take out the x, because they undo, but put absolute value around that x. And then square root of 4 simplifies to 2. Once we remove the absolute value, we can say that we have two solutions. We have x equals -2, and we have x equals +2. So I see over here that I already found an answer of x equals -2. So I don't have to box that again. It's just a double root. It's called a double zero. This is multiplicity of 2 because this answer occurred twice. So I'm just going to circle the other x equals 2. So these are my two zeros. All right, let's find all zeros of this equation. So f of x is 0. I'm not going to do grouping because I only have two terms. I am going to look for a greatest common factor. I can take out an x squared. That'll leave x squared minus 4. I'm going to go ahead and trade sides. All right, I know x squared is x times x, but I'm going to go ahead and separate, and I'm going to say x squared is 0, or x squared minus 4 is 0. Well, I could bring in the square root here and solve this using the square root property, but once I do all that, the only possibility for x is 0. Now, 0 occurs twice because of that exponent on x, but I don't need to write it down twice. I'm just going to write it down once. X equals 0. Over here, we've already solved that, so I'm not going to show all that work again. We saw that x equals -2, and we saw that x equals +2. So here we have three solutions, -2, 0, and 2, also known as x-intercepts, or roots, or zeros. All right, notice that each of these answers only occur once. I didn't have any repeated answers like I did up here. All of these zeros have what we call multiplicity of 1. They only occur one time. More about that when we get down here. Okay. All right, let's talk about multiplicity. Okay, so one thing we want to look for is when we're finding zeros, we want to look for multiplicity. Functions can have repeated zeros. We saw that. -2 occurred here, and -2 occurred here. Multiplicity is the number of times a zero is repeated. So for example, in this function, it can be factored into this binomial times that binomial. Notice that those two binomials are the same exact binomials. if you were to set these equations or these binomials equal to 0, you would have from the factor x plus 2, you would have a solution x equals -2, but then you'd have it again. So the same number twice. So we say that x equals -2 is a repeated 0. Okay. Because it's repeated twice, the 0 has a multiplicity of 2. Okay, so before I get down to this content right here, I want to go back up to our examples up here and actually go in and state the multiplicity of each of the zeros. So I'm going to put the topic of multiplicity here. Multiplicity. So for this example 1 right here, let's look at each of the zeros and state the multiplicity. Well, x equals -2. It occurred here from this factor, but x equals -2 also occurred right here from this other factor. So we say that x equals -2 has a multiplicity of 2. All right, here in a minute down here, we're going to see if that indicates that our graph at that x-intercept is going to cross or touch the x-axis. Right now, I just want to record this. If you have an even multiplicity, then we say that we touch the x-axis. So just write that down and we'll see in a graph here in the next video, okay, what's happening here graphically with this multiplicity. So x equals -2, multiplicity of 2 occurs twice, so we know that it touches the x-axis. The graph does, you'll see. All right, let's talk about x equals 2. That was another 0. Well, x equals 2 only occurred once, so we say we have a multiplicity of 1, odd number. So what happens when we have an odd multiplicity as opposed to an even multiplicity? Well, instead of just bumping off the x-axis and touching it, we actually cut through it. So we call that crosses the x-axis. Once we determine the zeros, we will be able to determine the multiplicity and if then graphically the graph crosses or touches the x-axis. So let's finish up in this video with defining the multiplicity of these zeros. All right, so the topic of multiplicity. So I have x equals -2, I have x equals 0, and I have x equals 2. And notice that x equals 0, well, we'll start with x equals -2. It occurs once. So we have an odd multiplicity of 1, which means that the graph is going to cross the x-axis. Let's go down to x equals 2. It's a multiplicity of 1 again, which means that graph at x equals 2 will also cross the x-axis. Okay, here's where it might get a little confusing. X equals 0, I only wrote it down one time, but let's look at the exponent on that 0. It actually has a multiplicity of 2 because x squared can be thought of as x times x. So each of those x's can be made to be a 0, so it really occurs, x equals 0 occurs twice, but I'm only going to write it down once. So what does that tell us when we have an even multiplicity? That we touch the x-axis. All right, so I know without looking at a graph that might be a little confusing, but once we look at a graph, it will all tie together. But we'll do that in the next video.